Hey guys, welcome back to the channel. Today we are looking at the A-Level October-November 2025 past paper. We will break down every single question step by step. It is super easy to follow. Grab your pen and paper, hit that like button, and let's jump right in. In this question, take that long number and chop it up into groups of 4, starting from the very back. When we do that, we get 3 neat little groups. The first group on the left is 1011, the middle group is 0011, and the last group on the right is 1010. Now we just turn each group into a regular number. Let's look at the first group, 1011. If we add up its place values, it gives us 11. The middle group is 0011. That one is super easy, it just equals 3. The last group is 1010. That adds up to 10. But wait, we have a tiny problem. In hexadecimal code, we cannot use 2-digit numbers like 10 or 11. It messes everything up, so we use secret letters instead. The number 10 becomes the letter A, and the number 11 becomes the letter B. So let's swap those numbers out for our letters. Our 11 turns into a B. Our 3 stays a 3, and our 10 turns into an A. Put them all together and boom, our final answer is B3A. In this question, we have the number 108. And we need to turn it into something called binary coded decimal, or BCD for short. Don't worry, it sounds way harder than it actually is. Computer scientists love using this trick because it makes numbers really easy for computers to read. So, how do we do it? Well, normal binary turns the whole number into one long chain of ones and zeros. But BCD is much cooler because it lets us take a shortcut. We get to look at each individual digit one by one. Let's break down our number, 108. We have a 1, a 0, and an 8. Now our only job is to change each of those single digits into its own little 4-digit binary code. We use the classic 8421 rule to do this. Let's start with the first digit, which is 1. To make a 1, we just put a 1 at the very end, so it looks like 0001. Easy, right? Next up is the 0. This one is a total breeze because 0 is just 4 zeros in a row, so we write 0, 0, 0, 0. Finally, let's look at the 8. To make an 8, we just turn on the first slot, which gives us 1, 0, 0, 0. Now for the final step, we just line up all 3 of our blocks right next to each other. When we glue them together, we get 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0. And boom, that is it! Look at this giant string of ones and zeros on the screen. 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0. It looks super scary, right? But don't worry, we can totally handle this. The question tells us this is a 12-bit 2's complement binary number. That sounds like a bunch of alien words, but it just means this is how computers write negative numbers. Here is the golden rule. If the very first number on the far left is a 1, it means the number is negative. Since ours starts with a 1, we already know our final answer will have a minus sign. Now let me show you a super easy trick to find the actual number. We are going to play a game called Flip and Add. Step number 1 is to flip all the numbers. Every time you see a 1, turn it into a 0. Every time you see a 0, turn it into a 1. Let's do it together. Our long number completely flips over and becomes 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. Step number 2 is number 1 to the very end of our new code. When we add 1 to those last 2 ones, it changes the end of our number. Our code becomes 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. Now for the final part. We just need to figure out what this new number actually means in regular math. We look at the spots where the ones are hiding. We have a 1 in the 4's place and another one in the 64's place. Let's add those two numbers together. 64 plus 4 gives us 68. But remember our golden rule from the very beginning? The original code started with a 1, so it has to be negative. We just put a minus sign right in front of our 68, and boom! Our final answer is negative 68. Look at this question. First up, we need to add these 2 rows of numbers. In binary, we only use zeros and ones. So 1 plus 0 is 1, easy peasy. Let's move from right to left, just like we do in school. In the very first column on the right, 1 plus 0 gives us a 1. The next column is another 1 plus 0, so that is another 1. Then we have 0 plus 0, which is just 0. Next is 0 plus 1, giving us a 1. Now here is where the magic happens. 1 plus 1 equals 2, right? But since binary doesn't have the number 2, we write down a 0 and carry a 1 over to the top of the next column. In that next column, we have 1 plus 1 plus our extra carried over 1. That makes 3. So we write down a 1 and carry another 1 to the next column. Moving left again, 0 plus 1 plus our carry makes 2. So we write a 0 and carry the 1. Finally, 1 plus 0 plus our carry makes 2 again. So we write a 0 and pop that last carry right out to the very front. Boom! Our final answer is 1, 0, 1, 0, 1, 0, 1, 1. But wait, look closely at that answer. Let's count how many digits we just wrote down. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 digits total. That brings us straight to the second part of the question. The problem tells us we are using an 8-bit register. Think of a register like a plastic toy box that can only hold exactly 8 toys. We just tried to stuff 9 toys into an 8-toy box. That extra number on the far left has absolutely nowhere to go, so it just spills right out and gets completely lost. Computers call this an overflow error. It happens whenever a math answer is simply too big for the computer's memory box to hold. And just like that, you solve the whole thing. In this question, we have this cool chart called an ER diagram. It is basically a map that shows how different groups of information talk to each other in a computer database. The problem wants us to connect 3 boxes: student, placement, and company. A placement is just a fancy word for a student working at a temporary job to learn skills. To connect these boxes, we use a special drawing called crow's foot notation. Why is it called that? Because the lines look exactly like a little bird's foot. The single line means one, and the bird foot means many. Let's read our hints. Hint number 1 says one student can have many different placements, but a placement only belongs to one student. That means student is the one side, and placement is the many side. So, grab your digital pen. Draw a straight line starting at the student box, and right before it touches the placement box, split it into a 3-pronged bird foot. Boom! We just made a one-to-many relationship. Now for hint number 2. It says one company can host many placements, but each placement only connects to one company. This is the exact same rule. Company is the one side, and placement is the many side again. Let's draw another line. Start a straight line at the company box, move up toward the placement box, and end it with another little bird foot right on the edge of the placement box. Look at that, our diagram is totally done, and we just bagged 2 easy points. Now let's roll over to part B. This one asks us to explain why our database is in something called third normal form, or 3NF for short. This is just a fancy computer science way of asking, why is this database organized so perfectly? To be in the third normal form, a database has to pass 3 strict tests, like levels in a video game. Our answer needs to show that this database passed every single level. First, it passes level 1 because all the data is broken down into its smallest possible pieces. No messy repeating groups are allowed here. Second, it passes level 2 because every extra piece of information connects perfectly to the main key of the table. There are 0 partial dependencies. Finally, it clears level 3 because there are no sneaky transitive dependencies. That means the extra information only cares about the main primary key, and it does not depend on any other random pieces of information in the table. Take a look at this table on the screen. It is called the placement table. It stores info like student IDs, company names, start dates, and whether the job is done or not. That last part is under the column called complete, and it just says true or false. Let's dive into the first question. It asks us to write a quick script to delete all the jobs that are already finished. When we want to wipe out data in a database, we use a command called delete from. So we start by typing delete from placement. But wait, if we stop there, we will delete the whole table. We definitely do not want to do that. We only want the finished ones. So we add a filter using the word where. We say where complete equals true. Put a little semicolon at the end, and boom, you just cleaned up your database. Now let's tackle the second question. This one wants us to count the total number of finished jobs for a specific student at a specific company. The student ID is LDEA01, and the company ID is NEAM. To count things, we use a handy tool called count. We start our script by typing select count star. That star just means count every row that matches our rules. The question also says we need to give this count a nice name, so we type AS total completed. Next, we tell the computer where to look by typing from placement. Finally, we need to set our rules using that trusty where clause again. We have 3 rules this time, so we glue them together with the word and. We type where student ID equals LDA01, and company ID equals NEAM, and complete equals true. Don't forget to put single quotes around the text code so the computer understands them. Let's look at the database example on our screen. We have 3 main lists: a list of students, a list of companies, and a list of job placements. The placement list connects the students to the companies. Now here is where our matching rule kicks in. First, let's look at the students. Every student has their own special student ID number. When we want to put a student into a job placement, we have to type their ID into the placement list. Referential integrity is the digital bodyguard that steps in and says, hey, you can only use an ID that is already on the main student list. You can't give a job placement to a ghost student who doesn't even exist at the school. The exact same rule applies to our companies. Every company has a company ID. When we log a job placement, that company ID must match a real company on our main company list. The database simply won't let you send a student to work at a made-up business. And that is literally all it is. Referential integrity just means you can't have loose, unconnected data floating around. It keeps all your tables talking to each other perfectly so your information never gets messed up. In this question, let's look at the mystery sentence at the top. It says x equals not, then a big bracket with A NAND B, XOR, and then not A or not C. Wow, that is a mouthful. But think of it like a recipe. We just need to check the kitchen tools, which are our logic gates, to make sure they mix the ingredients in the exact right order. Let's trace it out step by step like a detective. First, look at the top wire labeled A and the middle wire labeled B. They go straight into a NAND gate. That part looks awesome and matches our recipe perfectly. Next, let's look at the bottom part. We have wire A splitting off and going into a NOT gate. That gives us a fresh batch of NOT A. Then wire C goes into another NOT gate, which gives us NOT C. Now look closely at the gate where those two mix together. At first glance, it might look a little bit like an AND gate, but don't let it trick you. It is actually an OR gate. Since it is an OR gate, it perfectly combines our ingredients to give us NOT A or NOT C, just like the recipe asks for. Because that gate is doing the exact right job, everything else flows beautifully. The outputs from our first 2 steps go straight into the XOR gate, which looks like a shield with a cool double line. Finally, the whole thing shoots through one last NOT gate at the very end to flip everything upside down. And boom, that gives us our correct final answer, X. In this question, we have a truth table here with inputs R, S, and T, and an output called Q. Our goal is to write a logic expression for Q. So where do we even start? Here's the big secret. You only need to care about the rows where the output Q is equal to 1. Let's look down the Q column together. Scan it with me. Ah, look right there. In the second row, Q is a 1. And if we keep going down near the bottom, Q is a 1 again. Those are our 2 winning rows. Now, let's break down that first winning row. Look at the inputs for R, S, and T. R is 0, S is 0, and T is 1. In computer talk, a 0 means not and a 1 means yes. So for this row, we write down not R and not S and T. That is our first piece of the puzzle. Let's find the second piece by looking at our other winning row near the bottom. For this one, R is 1, S is 1, and T is 0. Using our same trick, that gives us R and S and not T. We are so close. Now we just have to glue these 2 pieces together. Since either of these rows makes Q equal to 1, we connect them with a big OR. So let's put it all together. The final answer is Q open parentheses not R and not S and T, close parentheses, or open parentheses R and S and not T, close parenthesis. We have a row of boxes holding 0s and 1s. Look at that group of 1s in the top row. Now look at the bottom row. See how those 1s hopped over to the left? Let us count how many boxes they jumped. 1, 2. Yep, they moved exactly 2 spots to the left. So how do we tell a computer to do that? we use a secret shortcut code called an instruction. Since the numbers move to the left, we use the letters LSL. That stands for Logical Shift Left. It just means we slide all the numbers over to the left side like a conveyor belt. But wait, we also have to tell the computer exactly how many steps to take. Since our numbers jump 2 spots, we just put a hashtag and the number 2 right after it. Put it all together, and you get LSL hashtag 2. First, let's look at what we have inside the computer's memory box, which is called the accumulator. Right now, it's holding a secret code of 8 numbers. It's 11000011. Got that? Awesome. Now, the question asks us to do a special trick called an XOR with the number 12. But look closely at that tiny symbol before the 12. That little symbol means the 12 is written in a special code called hex. Before we can do anything, we need to turn that hex 12 into regular computer language, which is just ones and zeros. To do that, we split the 12 into 2 parts, the 1 and the 2. In computer code, a 1 is 0001, a 2 is 0010. Put those together, and our secret number 12 becomes 0001010. Now comes the fun part, the XOR game. The rule for this game is super simple. We line up our 2 rows of numbers and look at them 1 column at a time. If the 2 numbers are different, like a 1 and a 0, the answer is a 1. If the 2 numbers are exactly the same, like 2 1s or 2 zeros, the answer is a 0. Easy peasy, right? Different gives us a 1, matching gives us a 0. Let's go through it from left to right. The first column has a 1 and a 0. They are different, so we write down a 1. The second column has a 1 and a 0. Different again, so write a 1. The third column also has a 1 and a 0. Different, so write a 1. The fourth column has a 0 and a 1. Still different, so write another 1. Moving to the fifth column, we have a 0 and a 0. They match, so we write down a 0. The sixth column is a 0 and a 0. They match, so write a 0. The seventh column is a 1 and a 1. They match too, so write down a 0. Finally, the last column is a 1 and a 0. They are different, so we write down a 1. When we put all our answers together, we get our final code, 11110001. In this question, we have a row of boxes called an accumulator, or ACC for short. Right now, it holds a secret code of 1s and 0s. The code is 11100011. Now, the computer gets a special command. The command says and 63. This means we need to compare our secret code with the number 63. But wait, computers only speak in 1s and 0s, so we need to turn the number 63 into computer language first. To do that, we write 63 as an 8-bit binary number. That gives us 00111111. Next, we line up our 2 rows of numbers right on top of each other. We are going to play a game called AND. In this game, a slot only gets a 1 if both numbers in that slot are a 1. If there is a 0 anywhere, the final answer for that slot becomes a 0. It is like matching puzzle pieces. Let's check the slots from left to right. The first slot has a 1 and a 0. That is not a match, so we write a 0. The second slot has a 1 and a 0. Another 0. The third slot has a 1 and a 1. It is a perfect match, so we get a 1. The fourth slot has a 0 and a 1, so that is a 0. The fifth and sixth slots both have zeros, so they stay 0. Now look at the last 2 slots. They both have 1s matching with 1s. That means they both get a 1. When we put all our new pieces together, we get our final answer. The box is now read 0, 01000011, and that is it. Let's look at our starting number. We have a box at the very top called the ACC, which is just short for accumulator. Inside it, we have the binary code 11100011. Got that locked in your brain? Awesome. Now the question tells us to do a trick called OR 100. This means we need to go on a quick treasure hunt down to address number 100 in our memory list. Let's look at the chart. If you follow the numbers down to 100, you see the secret code 00110001. Perfect. Now we have our 2 codes and we are going to play the OR game with them. The rule of the OR game is incredibly simple. We look at the bits line by line from left to right. If either the top number or the bottom number has a 1, then the final answer gets a 1. The only way you get a 0 is if both numbers are 0. Easy peasy, right? Let's do it together line by line. For the first spot, we have a 1 and a 0. Since we have a 1, the answer is 1. For the second spot, same thing. A 1 and a 0 gives us a 1. In the third spot, we have a 1 and a 1. That definitely gives us a 1. In the fourth spot, we have a 0 and a 1. That still gives us a 1 because at least one of them is a 1. Now look at the fifth and sixth spots. Both numbers are zeros for both of those spots. Since there are absolutely no 1s there, we have to write down 0 and 0. Finally, for the last two spots, we have 1s across the board, so those both turn into 1s. When you put that all together, our shiny new code is 11110011.